Let's find out the time period of SHM of a simple pendulum. We know that a simple pendulum is a bob which is tied up at one end of an ideal and extensible string of length L, and the bob mass is M. In this situation, at equilibrium position, we can simply state the tension in the string will be just balancing the weight of the block. So we can write at equilibrium position T is equals to mg. There is no need to mathematically further analyze the equilibrium position, as we are already aware about it is vertically below the suspension point. Now we displace the particle, the bob of this pendulum, by a distance x or by an angular displacement theta, and if we release it, then due to mg, a component of mg, it will have a tendency to come back. We can state again the tension will be changed and it will be acting at some angle theta. Now in this situation, this angle is also theta, so mg cos theta component will be balancing the tension, and in this direction the force which is acting is mg sin theta, and this mg sin theta is responsible for bringing the bob back to its equilibrium position. So here mg sin theta will act as a restoring force. So we can state at a displacement x from mean position, if we calculate the restoring force on bob, is this restoring force can be written as minus of mg sin theta, as it is having a tendency to bring the bob back. Now in this situation, we know as for small theta, sin theta is approximately theta. We can take sine of an angle as approximately equal to the numerical value of the angle for small angles. So if x is small, we can state here for a small x, that is for small displacements, theta will be small, and the value of theta can be written as x by L, because x will be the arc length and L will be the radius of circle in which the bob is being displaced, and x can be approximated as a straight line for small values of theta. So in this situation, we can write this restoring force is minus mg. It can be written as theta, which can be substituted as a minus mg x upon L. Now if we find out the acceleration of bob, the acceleration of bob can be written as simply restoring force upon mass. So it will be minus g by L into x. Now comparing with A equals to minus omega square x, because for displacement x from mean position, the acceleration will be minus omega square x, and we get omega is equals to root of g by L, which is giving us time period of SHM as 2 pi by omega, which can be written as 2 pi root of L by g. This is the time period we use. I think this expression you might have studied in your early classes also. Now we have just reduced this with the following steps, which we have studied in the previous section. In sequence, let's study the equation of SHM for a pendulum bob. We can also analyze different cases for writing the equation of SHM. Say we start with the case 1, when bob is released from extreme position. This is a situation in which say we are having a pendulum of length L. The bob is displaced by an angular displacement, say phi, or say the displacement of bob from equilibrium position is A, where we can write phi is equals to A by L if we wish to relate amplitude with the angular amplitude or the angular displacement for extreme position. If we release it, will have a tendency to come back, and finally it will oscillate. So at t equal to 0, the bob was released from its extreme position. So we can say as at t equal to 0, particle was at extreme position. We can take initial phase of SHM to be alpha is equals to pi by 2. This we already studied at the time of analyzing SHM equations. So its equation of SHM can be written as y is equals to a sine of omega t plus alpha. Here amplitude a is given to us, sine of alpha we take as pi by 2, and omega we already analyzed that it is given as root of g by l. So the expression will be root g by lt plus pi by 2. So the final equation of SHM will be a cos of root g by l into t. Now if we just discuss about the second case for writing the equation of SHM, in which at t equal to 0, bob was given a velocity at a position. So if situation is like this, in which the simple pendulum is tilted by an angle phi, and at this angle it is thrown with an initial speed v0. Now in this situation, at an angle phi, if it is thrown with the initial speed v0, obviously when it will reach the mean position and overshoot, it will move to a larger angle, say it is delta, to which it will be reaching the other extreme position. So we can state in this situation the amplitude of oscillation will be more than the initial displacement of particle, which is say x, where x can be written as L phi. If L is the pendulum length and phi is the initial angle at which the bob was given a velocity. And here the amplitude we can very easily calculate, as we know that velocity of particle in SHM can be given as omega root of a square minus y square. So here the initial speed which is given to the particle is v0. Angular frequency of SHM we already know it is given as root of g by l multiplied by root of a square minus the initial displacement when the velocity is v0 can be written as x, or it can be written as L phi square. On solving this expression, we'll get the value of amplitude, which is root of L square phi square plus L v0 square by g. This is the amplitude of oscillation. So we can write the equation of SHM of bob can be written as, here equation of SHM will be y is equals to a sine of omega t plus alpha, where the amplitude is given by this expression and alpha is the initial phase, and at t equal to 0 the particle was located at an angle phi. So here we can write at t equal to 0 y was equals to L phi. At t equal to 0 the displacement of particle can be written as x, or it is L phi. So on substituting here we'll get L phi is equals to a sine alpha. If we substitute t0 and y L phi, so here alpha we are getting as sine inverse of L phi by a. But in this situation we need to just have a look whether we'll go for general solution or only this. So here you can see as the particle is coming towards equilibrium position, it could be possible that particle would be going away from equilibrium position. So here we can say if it is going away from equilibrium position, the angular displacement will increase, and then after reaching the extreme position it will decrease. So at this position, as it is coming towards the reference point, we must take that it is a position at which the phase angle will be more than pi by 2. So it must be given as, more precisely, alpha should be equals to pi minus sine inverse of L phi by A. That will be a general solution for this equation. I hope all of you can understand. If the bob will be given a velocity away from equilibrium position, we would have taken initial phase in this case as sine inverse L phi by A, whereas in this situation we'll take initial phase to be pi minus sine inverse L phi by A. So this final equation of SHM can be written as A amplitude will be given by this expression, sine of omega t minus L plus alpha, where A and alpha would be given by this expression and this expression respectively.